Now that we've discovered these relationships for dr dt and d theta dt, we want to apply them to the system we were looking at before. So we have r dr dt, and we want to say that that's x dx dt, so that's xy minus x squared plus y squared minus 4 times x squared. And then we want to add y dy dt, so that's going to be a minus xy minus x squared plus y squared minus 4 times y squared. Well, hopefully you notice that xy cancels with the minus xy. And so we're left with minus x squared plus y squared minus 4 times x squared plus y squared. And I seem to see a lot of x squareds plus y squareds floating around. We know that x is r cosine theta and y is r sine theta. And of course that means that x squared plus y squared is actually equal to r squared. Oh, so we can rewrite this as minus r squared minus 4 times r squared. Oh, now we can solve for dr dt. So dr dt dividing by r is minus r times r squared minus 4. And that equation is completely in terms of just r. Okay, let's think about theta. So r squared d theta dt, that's going to be x times y. So that's going to be a minus x squared minus x squared plus y squared minus 4 times xy. And then we want to add y times, subtract y times dx dt. So that's going to be a minus y squared. And then we're going to add, minus a negative there, we're going to add x squared plus y squared minus 4 times xy. Now hopefully you see that this term, which is negative, cancels with this term that is positive. And so what I'm left with is minus x squared plus y squared. But that's minus r squared. Okay, well that tells me that d theta dt is just negative 1. Okay, now I have an interesting system here, because dr dt is negative r times r squared minus 4. And d theta dt is minus 1. So the r equation just has r's in it, and the theta equation is actually constant. So we could actually solve the dr dt equation using separation of variables, but I just want to get an idea of what's going on here. Okay, so I'm going to look at just equilibria for dr dt. So I can think about that as kind of being like the r nullcline. So that occurs when r is 0 or r is plus or minus 2, but r as a radius has to be positive, so I'm only going to consider 2. So 0 and 2 are places where the radius doesn't change. Well, 0 makes sense because that was our equilibrium point, right? That was our equilibrium point, 0, 0. But 2 is interesting because at 2 we have that r doesn't change, but theta does change. Okay, so this is never 0. Okay, so we have here, we have that r remains 2. R is always 2. But d theta dt is negative, and that's actually a clockwise rotation. So let's look at the phase plane. And you can see we had this circle. And that was kind of like a steady state. I wouldn't call it an equilibrium. That is a steady state. And then solutions seem to be approaching that circular orbit or periodic orbit. But they also are approaching from the inside. And so it seems that r equals 2 is a stable, I won't call it an equilibrium, I'll call it periodic orbit. We could actually take the derivative of this with respect to r to show that it actually is stable. So what we found is that periodic orbit that we found when we were analyzing this solution. So we had a spiral source, and then things coming out from 0, 0 were attracted to this periodic orbit, but things outside of 0, 0 are also attracted to this periodic orbit.